So let's continue and actually verify that the set of integers modulo 12 actually forms a group under addition modulo 12. Namely, if we take this set of 12 elements, 0, 1, 2, etc., up to 11, and we take addition modulo 12, the claim is that this is a group. Now, verifying that this is a group involves some subtleties, so we're not going to go through all of the details since they can get a little bit tedious and difficult, but let's just kind of verify some of the basic ideas. So remember the axioms for a group. You were supposed to have a set along with some type of binary operation, some way of combining two elements to get a new element. And this was supposed to satisfy the conditions that it was associative, there exists an identity element, and there exist inverses. Namely, every element has an inverse. Associativity, basically, it kind of comes for free from the fact that when we define this addition modulo 12, remember how we defined it. We added two numbers in the ordinary sense of, ordinary addition, and then we looked at how many times 12 went into it, and then we took the remainder. So the fact that ordinary addition is associative, you can verify that this operation is in fact associative. So we're not going to do that. It gets a little bit messy to verify that, but it's true. So what about number 2? There exists an identity element. So this can be made most clear by just looking at an example. So let's take 5. So what we want to ask is, what can I combine with 5 to get 5 back, mod 12, right? So remember, the identity had this property that when you combine it with something else, it's like you haven't done anything. So in the context of symmetries of the square, the identity, we denoted that by the letter E. This was the do-nothing symmetry, where you simply did nothing to the square. And so if we did any type of symmetry and we composed that with the identity, we just got the original symmetry. So for example, if you did horizontal reflection and then compose that with the identity, you just get horizontal reflection. So the identity didn't do anything, so it always gave you back your other element. So in this case, 5 plus what gives you back 5, where plus is, the addition here is modulo 12. And it should make sense that this is just 0. If you take anything plus 0, you get it back mod 12. Not just this doesn't just work for ordinary addition, it also works for this mod 12 addition. Does there exist an identity element? Yes. And this is 0. Okay, what about inverses? So what does that mean? Again, let's use the case of 5. So the question is, what can I combine with 5 to get 0? Again, this is mod 12. So in the context of symmetries of the square, the idea is that every symmetry had the inverse. That was a way of thinking of undoing the symmetry. So for example, if you rotated by 90 degrees clockwise, then you could just rotate by 90 degrees counterclockwise to get back to the identity. Or another way of thinking of it is if you rotated 90 degrees clockwise, then you could rotate again 270 degrees clockwise, and combining those two rotations would give you a 360 degree rotation, which would take you back to the identity. So the idea is, we take 5, what can we add to it to get back to the identity, which is in this case 0? Well, how can I get 0 modulo 12? Well, remember, in this mod 12 arithmetic, we add two things. We divide by, we see how many times 12 goes into it, and we look at the remainder. And that's the answer we put right here. This is supposed to be the remainder. So we want a remainder to be 0. Well, the only way the remainder can be 0 is if 12 goes in evenly to our answer. So 5 plus what gives us some multiple of 12? Well, 7. So let's think about that real quick. 5 plus 7, in ordinary addition, that's 12. And now if we start to think of it in this modular sense, modulo 12, what do? We say 5 plus 7 is 12. How many times does 12 go into 12? Well, obviously goes once. What's the remainder? The remainder is 0. So what is 5 plus 7 modulo 12? It's the remainder, which is 0. So 7 is the inverse of 5. For this operation of addition modulo 12, the inverse of 5 is 7. So this is why it's very important, even though these things are numbers, right, 0, 1, 2, 3, 4, 5, etc., it's very tempting to say the inverse is negative 5. But notice that negative 5 is not an integer modulo 12. It doesn't belong in this set here, right? There is no negative 5 there. When we have to think about what our inverses should be, our inverses are defined by that property. That's why it's very important that when you are thinking about groups and identity and the identity element and inverses, you have to be very specific about what is the set of elements that you're working with and what is the group operation, and that makes all the difference. 7 is the inverse of 5, and likewise 5 is the inverse of 7. Because of the same thing, right? You'd be asking, what can I add to 7 to get to 0 mod 12? Well, it would be 5. So let's look at another example. Let's look at 9. So 9 plus what is 0 mod 12? So now you should be thinking, that's pretty easy. I take 9, what can I add to get to 12? Because in my system of integers mod 12, 12 is essentially 0, because 12 is really treated as 0. And so how can I take 9 and add something to get up to 12? Well, 3. 9 plus 3 is 12. So 9 plus 3 is 12. I divide by 12. Well, 12 goes into itself once. The remainder is 0. And so 9 plus 3 is 0 mod 12. So 9 is the inverse of 3. And likewise, I would say 3 is the inverse of 9. So for each and every single element, you can actually go through and find an inverse. And let's just write below this inverses. Right? So for each one of these elements, 0 through 11, let's write down what its inverse would be. So what would the inverse of 0 be? Remember, I want to add something to 0 to get 0 mod 12. 0 itself, so it's its own inverse. What about 1? What can I add to 1 to get 0 mod 12? Or another way of thinking of it, what can I add to get up to 12? 11. If I add 11 to 1, I get 12, and then if I look at the remainder, it's 0. What about 2? How can I get up to 12? Well, I can add 10. What about 3? How can I get up to 12? Well, we've already seen I can add 9. What about 4? 4 plus 8 is 12. The remainder is 7. So for 5, it would be 7. For 6, it would be itself. For 7, it would be 5. For 8, it would be 4. For 9, it would be 3. For 10, it would be 2. For 11, it would be 1. So those are the inverses of all the elements. So we've seen that the set of integers modulo 12 with addition modulo 12 is associative. There exists an identity element, namely 0, and every element has an inverse. So in fact, this is a group. And it's also very worthwhile to point out here that we did this, of course, with addition mod 12, but this in fact can be generalized. There's no reason we had to just use 12. We could have done the same thing for any positive integer. Namely, I could have talked about addition modulo 15. I could have talked about addition modulo 32, addition modulo 1000, addition modulo 85 billion. And it would have worked in the same way. I would have had a larger set of elements or a smaller set of elements possibly, but it would have been the same idea. Just as a quick example, let's think about Z5. This is the set of integers modulo 5. So the set of elements would be 0, 1, 2, 3, 4. And the operation we would want to consider is addition modulo 5. So how would that work? Well, the same way it worked above. Suppose we want to add 3 and 4, mod 5. Well, we just add them in the standard way. We ask how many times 5 goes into 7. 5 goes in once, but then there's this remainder. which is 2. And so we are just interested in that remainder. So 3 plus 4 mod 5 is 2. So it works exactly the same way as with mod 12. The only thing is, instead of seeing how many times 12 goes in and taking the remainder, we see how many times 5 goes in and we take the remainder. And we could ask, for example, what's the inverse of 3? Namely, 3 plus what is 0 mod 5. By the way, the identity here is still 0. You should be able to check that. So what about the inverse? 3 plus what equals the identity, which is 0 mod 5? Well, I want to add to get up to 5. 3 plus 2. 3 plus 2 would be 5. How many times does 5 go into itself? Well, once. What's the remainder? 0. So that's our answer. So 3 plus 2 is 0 mod 5. 2 is the inverse of 3. And likewise, 3 is the inverse of 2, modulo 5. And so we can see that there's nothing special about 12, there's nothing special about 5. For any positive integer, we can play the exact same game